Hi guys, I hope you guys are doing great. Welcome to lecture number 4 of operating system. I hope you guys have understood the concepts we talked about in lecture number 3. It was about processes. We talked about processes in a lot of detail, what a process is, how operating system manages processes, how kernel manages processes. Then we talked about how processes can communicate with each other. We called it inter-process communication, how there are different ways of processes to communicate. One was message sharing and the message passing, and the other one was memory sharing. So I hope you guys understood the concept. Few students already approached me about some of the concepts which they were not clear about. I really like that. So always ask questions about something you are not very clear. It's absolutely fine to ask questions. It's absolutely fine. Don't be shy. Don't hesitate asking questions, because as you see that our course flow is in such a way that it's building upon the previous concepts we have studied in the previous weeks. So it's very important that you guys understand what we have studied up till now so that we can move forward. And even in today's lecture you will see that we're going to talk about threads in week number 4 in today's lecture in this week. And you're going to see how threads are associated with processes, how they're associated with operating system, and so on. So if you understand what the processes were, it would not be very difficult for you to understand threads, because threads are actually sub processes, and we're going to see how they work and what they are, how they are different from processes, why operating system actually needs threads to perform different tasks, and why threads are very famous these days in modern operating systems. So we're going to talk about all these things, and as always we're going to do some exercises. We're going to implement some threads. We're going to see how the concepts we have studied are actually implemented. You will see that we'll do the exercise in C language, but I will tell you during the lecture, during the exercises as well, how you can use these threads in different programming languages also. So we will talk about exercise in great detail. We'll do a couple of exercises and we'll ask you to do some practice for some other exercises as well. As you can see in the last column, we have assignment 1 coming up. Wow, I'm excited about that. I'm not too sure about you guys. So we're gonna have an assignment this week as well. So I'm gonna explain assignment at the end of this lecture, and don't worry, it's not gonna be tough at all. It's gonna be easy. It's gonna be fun. If you understand today's lecture, you should be able to completely solve this assignment on your own. Obviously, I don't want anybody to help you solve that assignment, but if of course if you need help, I'm always there. Just drop me an email and we can discuss about that. Anyway, so we're going to talk about assignment, and at the end of the lecture as well, I'm going to explain each and every bit of that assignment as well, so that it's easy for you to understand what I actually want from you guys, what are the actual requirements of this assignment. And of course marks are important for the assessments, right? At the end of the day, your grades, your marks are very, very important. So I'm going to tell you the techniques how you can secure maximum marks in this assignment as well. And during the exercises of this week, I'm going to solve something very similar to what you're going to see in the assignment. So if you understand the lecture, if you understand the exercise we're going to do, assignment is just going to be a piece of cake for you. So please concentrate on the lecture and make sure you understand each and every concept clearly, and then we can talk about the assignment as well. So this is this, and let me show you quickly the assessments as well. Now if you see, and we have discussed this, that assignments are 30% of the course. So there are going to be 3 assignments, as you can see over here, and make sure whenever I change the slide, this dinosaur, it scares me. Anyways, so assignments are very, very important. 30% marks are for the assignment. So each assignment, as of my current understanding, is going to be 10% of your whole assessment, but we'll see. At least the first assignment is 10% of the whole course. So make sure you score maximum marks in these assignments and the project, so that you have good space to play with when it comes to final exam. At least you have secured more than 50% of the marks in the project and the assignment, so that you can easily go to final exam and score accordingly in your final exam. So it's very, very important that you get maximum marks in assignments and project, as many marks as possible in assignments and project, and you can do that. So please concentrate on that as well. So having said that, let's move to our lecture. Our today's lecture is about threads, and what threads are, why operating system needs threads, why modern operating systems they like threads, why programmers like you and me we like threads, how they can help us, how they can solve a lot of problems for us. And you will see some examples how modern operating systems are using thread to solve a lot of problems which we I mean, we don't face them anymore because operating system has solved those problems through said threads. So you will see how to do that. So let's talk about thread. What a thread is. Well, thread is just a basic unit of your processor. So if we call thread a sub process, it's not wrong. So thread is basically a basic unit of your processor, a process, and we know what a process is, right? So process is a part of a program that is in the memory. Again, a process is a part of program that is inside the RAM, ready for execution or waiting for something. We know there are different stages or different states of the process. So whatever the state process is in, it still is a process. And thread is actually just a part of that process. So a process can have many threads. A process can have only one thread. But a process will have at least one thread. I mean, at least in modern operating systems, in all the modern operating system, a process will have at least one thread in it, right? So we'll talk about what single thread processes are and what multi-threaded processes are. We'll talk about that. So again, thread is just a basic unit or a sub process, right? That is in the memory. If something is not in the memory, it's not a thread, it's not a process, it's a simple program, right? Or it's a simple file, right? So that's a thread, and after a couple of slides I will show you the difference between a thread and a process, so it will clear up all the confusion what a thread is, what a process is. So we'll talk about that in a while. So as I said, a process can have a single thread in it, a process can have multiple threads in it, but process should have at least one thread in it, at least in the modern operating systems. And what thread comprises of, just like processes, I mean, it has less things than a process has. So a thread has a thread ID, it has a program counter, just like what we have in our processes. It has some registers and it has the values of that registers, and then it has stack for storing some temporary temporary variables. So we know what a thread is now, and as I said, in modern operating system, and not even only in modern operating system, but in our modern applications, you'll find multiple threads. Even in Microsoft Word, for example, let's take that example once more. So let's take a browser example, since we have been taking Word example for quite some time now. Let's move to a browser example. So for example, you have not Microsoft Edge. Let's take Chrome, right? So what Chrome does normally is, whenever you open a tab in a Chrome, it creates a new process, right? I'm just giving you an example, although Chrome doesn't do this, it's quite complicated. And you open another one, it will open another process for you. But in modern versions of Chrome, how it works is, when you open a Chrome window, that whole Chrome window is actually one process. It actually is one process. It considers it as one process, and different tabs, it takes them as different threads, right? Now it again depends upon different version of Chromes, but just to hide all the complications of Chrome, how Chrome works, how different processes and add-ons and so on work in Chrome, just to give you a simple example, if we consider a Chrome example, then Chrome window will be a process for you, and different tabs inside it can be different threads for you. Or if we consider the other versions of Chrome, where Chrome tab, a browser, inside browser, a Chrome tab is considered as a process. When you go to a web page, your web page might be looking for different images, it might wants to download some video, it might wants to show you some text messages, or JavaScript wants to run. These can be different threads within your processes, right? And we're going to talk about threads in a while in more detail, and you'll get to know what they are. So but for now, you can know that a thread is just a part of a process that does something on behalf of a process. Now we have been talking about threads. So what thread normally is used for is, is to do something on behalf of a process, because you cannot have a process do everything on its own, right? Just like you cannot have a program do everything on its own. If, for example, if there were no processes and program has to do a program had to do everything, you had to load the whole program into the RAM, right? If assuming there are no processes, and that will just fill up all the memory, all the RAM, assuming that today's programs or applications are very heavy in their size and they are doing so many different things. So you have to load everything in the RAM if there were no processes. In order to solve that problem, operating system developers, what they did is they said that, okay, no need to load the whole program into the RAM. Let's take some chunk of that program and load that into memory. And they started calling that a process. Okay, we know up till here that this is the difference between a program and a process. Now, when there is a process might need to do different things. For example, I gave you an example of Chrome. Chrome might want to translate a web page from one language to another language. It might needs to download some images from another external website. I'm talking about one Chrome tab. It might needs to run JavaScript. So if the one process is going to do all these things, it's going to be very difficult. And again, same problem will occur, that okay, if one process is doing, for example, it's running a JavaScript, then our processor will be busy running JavaScript. What about other processes, downloading the image or translating from one language to another? Those tasks, they need to wait unless and until the processor is done with the first task that was provided by the process, right? So in order to solve this problem, in order to make your computers run fast on multi-core programming, we'll talk about multi-core programming as well in coming slides. For multi-core environments, since we in our modern computers, we know that there are different cores, there are different processors. There is not only one processor, there are different processors, so that we can do multiple tasks at the same time. So in order to take advantage of that, if there is only one process doing everything, then other cores will be idle, right? Assuming there is only one process and there are four processors. Now one process is running and one process is running on one of the processors, and other three processors are just idle, right? So we cannot use this flexibility of using different cores or different processors. So in order to do that, what we do is we split our process to further smaller units. We call them threads. So for example, there is process 1, P1, and it has 3 different threads. One thread is running JavaScript, one thread is downloading images, and one thread is translating from one language to another language. So since there are 3 threads within a process, processor 1 can take one of the threads, processor 2 will take the second thread, and processor 3 will take the third thread, and processor 4 will take some other program, or so on. In this case, our one process can now be subdivided into different threads, and those different threads can work on different processes. How this will help? Of course, our program will run much faster, because our tasks, they don't have to wait for the previous task to finish. They can run simultaneously, they can run at the same time. I hope it clears what a thread is now. So let's move further now. Now, as I just mentioned that threads can be used to do a lot of things. For example, they can be used to update your display. For example, I just gave you an example of images, some of the images your web page wants to display. So in your code, for example, you have written that code in JavaScript or ASP.NET or whatever. Now when the update display or show images code comes, then obviously it will go and fetch those images from the server and then tries to display that. But this fetching might take some time, right? It will go to server, fetch information. What about the other things that are in line to be run, right? If there was no threads, then this will keep on running until all the images are fetched for the web browser for that web page, and then next thing will start working. For example, spell checker is next one, for example, or fetch data was next one. So if there was only one thread, then obviously this task has to finish, only then next task will work, and then next task will work. But then in order to solve this problem, what we can do is we can divide these three tasks into different threads. So this is one thread, this is thread number 2, this is thread number 3, and we can assign this thread number 1 to processor 1, this one to processor 2, and this one to processor 3, and if there is another one, we can assign it to processor 4. So they can run simultaneously at the same time, which will increase the speed, which will increase the efficiency as well. So that's why our processes are normally called heavyweight processes, and threads are normally called lightweight. And we'll talk about, we have already talked about some of the attributes why they are called heavyweight processes. Obviously they have a lot of other things to do. If you remember last time we saw process control block that contains a lot of things inside, right? It contains priority, it contains ID, it contains open files and so on. If you remember the diagram I showed you of process control block, it's a very heavy process control block that contains a lot of information. But sometimes we don't have to load all this information to our processor to be executed, right? So we don't want that. We want only small portion of that process to be loaded into the RAM so that that can run, and that small portion is normally called a thread. That's why thread creation is lightweight, process creation is heavyweight. Why process creation is heavyweight? Because process creation needs a lot of information to be stored in the process control block, ID, open files, and then states of the process, moving from one state to another state, and so many other things. But thread does not require a lot of things. If you see, thread contains fewer things. These are few of the many things thread contains, but it is still less than what a process contains, right? So that's why it's pretty lightweight. And then obviously once we divide our process into different threads, our code is easier to read. It becomes much simpler. Instead of having all the things run in one process, we can split them to run in different threads, and we will see in today's program how threads can actually help, how we can take the pain from the process and divide that to different threads. So all of the things, process doesn't have to do it on its own. We can split that into different threads, right? And we will see how to do it today. Then kernels normally they help in multi-threading. Our modern kernels, they are almost all of the kernels, they support multi-threaded environments. So we will see how they support that. Let's take another example of multi-threaded server architecture. What happens is, let's assume this is a Google server. Let's assume this is a Google server. Now on this server, people are coming for their queries, for their search queries. They are entering search queries, and the results are returned to the client. So let's assume the first client came, and let's assume there were no threads. There is only one process, and the server, let's assume it will never happen like that, but let's assume that there was only one process which had only one thread. So first client came, it tried to search for UFV, for example. What server will do is, it will initiate its default thread, and it will fetch the information. This thread will fetch that UFV information and return that information to the client. So what about while this thread was fetching the information, second client came and it asked for a query Canada, for example. So this thread is busy, so the second client has to wait. So it will take ages for the second client to get its turn, right? But on Google it doesn't work like this. You will see that your requests are returned, your query or your search results are returned in milliseconds, right? It's so fast, it's very, very fast. So how they are doing that? What happens is, the server contains multiple threads, right? So one client request is taken by thread 1, client 2 request is taken by thread 2, and client 3 request and so on are taken by thread n, and so on, and the results, and these threads will return the results accordingly, and those results are returned to the clients. So this is how multi-threaded server architecture can actually help in giving response to client requests, right? So it becomes very, very easy, and I showed you, if it's not there, how it can really hurt the performance of a server, because the clients have to wait, and if they have to wait for 5, 6, 10 minutes, then they will never come back to the search engine. And this is just one example, and this is just a Google example I gave you. Imagine this is a mail server, and people are fetching their mails from this mail server. It can be Gmail, it can be Hotmail or Yahoo, If one guy has 10 emails at a time and there is only one thread, then this thread will take forever to fetch those 10 emails from the server and returning that to client. What about other clients that are looking for their mails at the same time? They will have to wait, right? So this server can be any server. So these days, not only operating systems, but based on the operating system performances, the performance of the servers are improved because of multi-threaded server architecture. And this is how a multi-threaded server architecture looks like. I hope this is clear now and we are clear about what threads are. Let's talk about some benefits of threads. I have already shown you, explained you some of the benefits. Let's talk about some more benefits. Responsiveness. Responsiveness, what it does is, for example, in our graphical user interface these days, graphical user interface of operating systems and most of the applications, they are using threads. How they are using threads? Now let's assume you have created an application. What that does is it asks for username and password. So as soon as your user double clicks your application's icon, a small window appears that asks for your users to enter a username and password, right? So it asks for that. So as soon as user enters the username and password, it will go to the server, fetch your credentials, and if they are correct, they will let you enter the application. Otherwise, they will show you an error or so on. So if you have noticed that all the applications that are doing something like that, what they do is, at the same time, when users enter username or password and click the login or sign in button, what happens is there is normally a wheel icon or a wait icon that is shown to you. But if you see, that icon is normally animating, right? It's animating. It's not very static. So what it means, and at the same time, when that is happening, you can still work on some other application. Your user can work on some other applications, right, at the same time. So what these things are doing is they are running on different threads. If your thread was bringing your credential, your user's credential from the server, that thread was only one process in your operating system, then you could have not touched anything else because your processor is busy helping your user in logging into your application if there was only one process, right? But that process was then spread into different threads. First of all, there are different threads. So one process was handling your application in the operating system, one was handling the network connection, one was handling your maybe word browser or whatever, word processor and so on. So there are many processes running. But let's go back to your application when user was signing in. At the same time, when user was signing in, you could see that there is an animated icon which is appearing, which means that your one of the threads of your application has actually gone to the server, or it's in process of communicating with your server and fetching information from that. And another thread in your application is actually showing you that animation, which is telling you to please wait, or a blinking icon or a blinking text that is telling you actually to please wait, we are fetching your information, right? And then sometimes some applications are more user friendly. What they do is they actually show you we are almost there, right? Or we have fetched your information, or 1 more minute left, or something like that. Or sometimes they show progress bar as well. For example, sometimes when you are installing applications, what they do is normally they show you the wizards, they normally show you how much the application has installed and how much time is still remaining, right? Now what that is doing in the background, it has multiple threads running. Some of the threads, they are installing, they are copying the file, some of them they are connecting you to the internet, and one of the thread that is on the graphical user interface is actually showing you the progress bar, right? It's showing you the progress bar. So that's how your responsiveness, or that's how your threads help in responsiveness. So on user interface, some of the things are happening in the background, so those threads are working in the background, and your user interface is not blocked, so you can still interact with your application, your interface, right? So you can click a cancel button, for example. You can still click a cancel button if you don't want to sign in, or if you don't want to install an application. So it means that you can still interact with your user interface. If there was only one process and no thread, or there was only one process with the default one thread, then that thread was busy fetching your information, then your user interface will be blocked or frozen. You cannot do anything because the thread that allows you to interact with your user interface is now busy fetching your information. So you cannot click the cancel button, your user interface will not update, it will not show you the animated bar, it will not show you anything. And that is actually happening in your current modern operating systems as well. So while I am downloading a file, I can still play with other things, right? So one of the threads is, for example, downloading my file. The other threads are helping me do a Microsoft Word work, right? Inside Microsoft Word, obviously the process, inside process, I have different threads. So these are different things that are happening at the same time. So you don't have to wait for one of the tasks to complete before you move to other tasks. That's why you can take benefit of multi-core environment or multi-processor environments, right? So this is called responsiveness, where you can take benefit of threads to make your interface more responsive to you, instead of just getting stuck at its current position, right? So next benefit of a thread is resource sharing. Well, since I will show you a diagram in a while as well. So what happens normally is your threads from one process can share resources. For example, you have a process called process A. It has 3 threads: thread 1, thread 2, thread 3. Now, since these three threads are part of one process, they can share information with each other. They can share the resources of the process, or if this process has asked operating system to share printer, your threads can share that printer, right? Similarly, the memory that process is using, your threads can share that memory as well, and we'll see what other things your threads can share. So threads can share resources with each other as well, and since they can share resources with each other, they can communicate with each other much more easily than the processes. If you remember, we used message passing or memory sharing in inter-process communication, but for threads it's not that complicated. They share resources, they share space. That's why they can communicate with each other without any worries. And then economy is not only financial all the time, it's the efficiency, it's the time, it's the effort required to program a thread and a process. So it's much more cheaper to create threads than the processes. So in order to create a process, it takes a lot of overhead, but for thread it doesn't take too much time. Even when you are doing a context switching, if you remember last time we talked about context switching, if you are context switching a process, it's much more expensive than context switching a thread. So switching threads is much easier than switching processes. So when it comes to economy, threads are much better than the processes, and that's actually one of the reasons why threads are there. Otherwise there was no need of threads. Then scalability, obviously if we have multiple processors, and if we can split our process into multiple threads, each thread can be entertained by one of the processors, and it becomes very easy to scale your application or in general your operating system. So these are some of the many benefits of the threads, and it's a very, very important topic when it comes to your assessments and your exams as well. So do understand the difference between, I'm going to show you the difference between threads and processes also, and what are the benefits of threads over processes, right? So we need to know all these things. So let's talk about what a thread is and what a process is, and what are the main differences between them. So we know that a process is a program in execution. Any program that is in memory is a process, right? That is called a process, and thread is actually a small part of that process which is in the RAM, right? So this is the difference. So a process is a small part of a program, and a thread is actually a small part of that process. So thread cannot, in general we can call a thread a small or a tiny part of a program as well. But obviously threads are not coming directly from a program. Threads are actually coming from a process. So if we ask you a question that is thread in the RAM, or it can be passive as well, it can just stay on the disk. Well, threads cannot stay in the disk, they have to be in the RAM, right? Unless and until there is a need to do that. So this is one of the differences, what thread is, what a process is. We now know that a process is a small part of a program and thread is a small part of a process. Then we already talked about this, that threads are lightweight processes and processes are heavyweight, obviously, because of the process control block as well. It contains a lot of things. Processes contain a lot of things in their process control block, and there is a lot of overhead when doing context switching, because they have to save a lot of information. Processes have to save a lot of information when they are switching between different processes. However, threads, since they do not carry a lot of information with them, they are very lightweight, and while doing context switching, it's not that heavy when we are doing context switching, because not a lot of information is associated with threads. Obviously, threads will take less time to create because you don't have to provide a lot of information to them. Processes that do take a lot of time to create because a lot of information needs to be provided to them. Obviously, even for terminating, threads take less time to terminate. Processes do take a lot of time to terminate as compared to threads. Then, as I said earlier, threads take less time for context switching. Processes take more time for context switching. Obviously, threads consume less resources because they are lightweight. Processes do consume more resources because they are heavyweight. And then threads have their own PCB, I mean parents PCB, they work on parents PCB, and they have their own thread control block, just like process control block. And I showed you the components inside the thread where they contain a stack, and I will show you a diagram in a while as well. And process, as we have discussed in the last lecture as well, that they have their own PCB, process control block, and the component and the stack and so on. So these are the major differences between a process and a thread, and I'm sure it's much more clear now what a thread and a process is, and you can easily tell a difference between what a process is and what a thread is. And when we do the exercise, since we have already done a couple of exercises for processes, when we do the exercise for thread, you will get to know even more that how threads are more beneficial than processes. I'm sure with theory you can tell as well, with all these key points that thread has over processes. So these are some of the differences between threads and the processes. Let's see a little bit how process shares its memory with threads and what single threaded and multi-threaded processes are. Let's talk about single threaded processes on this diagram. So this is a whole process. This is one process, and this process is a single threaded process because it contains only one thread inside. It has only one thread inside. So with one thread inside, a default thread inside, obviously this thread has access to registers, process registers, stacks, files, data, and code, and so on, right? So it has only one thread, as compared to multi-threaded processes where we have, in this case, 3 threads in a process. So this is the whole process, and inside this process it has 3 different threads. If you see these 3 threads, they share the code, data, and files of this process, right? For this process. So thread 1, thread 2, thread 3, they share code, data, and files. So if they have to communicate with each other, they can even easily communicate with each other because they share this space of the process, right? But each thread has its own stack and it has its own register sets, right? So just like what you see in the diagram, so thread 1 has its own stack and register because it has its own variables to store, and it has its own information to store in the register. Thread 2 and thread 3, they have their own stack and registers. So let's talk a little bit more about what multi-core programming is, or what multi-core or multi-processing environment is. So multi-core or multi-processor systems, normally they are the type of systems in which we have multiple processors in our system. So these days in our modern computers, we do not only have one processor, we have multiple processors. So we have dual core or quad core processors in our computers that help us improving the efficiency of our programs, the speed of our programs, and they actually help in overall performance of the operating systems. So with these hardware improvements, our software, majorly our operating system, needs to improve a lot so that it can use the benefit of these multiple processors, not only when performing operating system tasks, but allowing different applications, third-party applications, to take this flexibility and freedom of using multiple processors on the system. When it comes to third-party applications and using these multi-cores or multi-processor systems, it becomes a responsibility for a programmer or a developer of that applications to get benefit out of these multiple processors and multi-core systems. So when it comes to programmers and developers, it also becomes challenging because you need to then identify the tasks so that you can let your certain threads perform some of the tasks and let other threads perform some other tasks. So since these multi-processors have multiple processors in them, you can allow some of the tasks to work on one of the processors and the other ones on the other processors, and it is your responsibility as a programmer to decide how many threads you are going to have in your program or in your process, in one process. Before obviously that, how many processes you are going to have in your program and how many threads inside each process you are going to have, and you have to keep a balance. You cannot just keep on creating threads which are not required, and we'll talk about why it's important to keep a track of your threads, why it is important to keep a balance of your threads. Then splitting the data. For example, thread 1 wants to read a file, and it has to read a very lengthy file. Then you might want to split that task into different threads. For example, one of your threads or one of the requirements of your program is to read records from a database that has 1 billion rows, so it's a lot of record. So what you can do is, if you allow one of your threads only to read all this information, it will take forever. Even if your computer is very fast, it will take forever. So instead what you can do is you can split your process into multiple threads. For example, if you have 4 processors in your system, you can split your your process to read data from the database into 4 different threads. Maybe one of the thread starts from record number 500,000 or from somewhere, so you can put a pointer to each of the thread so that it can start reading from a certain point in your database, and other threads can start from some other point, so that your process or your program doesn't have to wait for very long for your data to be read. So you can take this type of approach when you are programming your programs. So it's important that you know as a programmer what approach you need to take when you are trying to take benefit or advantage of multiprocessor systems. Then data dependency. Obviously your program, in your program, for example, if you want to, I just gave you an example of reading the records from a database, and you want to perform some task. Now before reading the data from the database, you cannot perform certain task on that data. For example, you want to clean your data or something. If you don't know the data, you cannot perform some other tasks on that. So sometimes your data might be dependent on some other tasks. So your threads might be dependent on some other threads. So this is also your responsibility as a programmer to make sure that whatever you are doing, it has all the dependencies available before the task is actually assigned to your processor. Then testing and debugging. Obviously you have to make sure that whatever you are doing, you test that and debug that if there is any errors, and only then launch your program. So it's a great responsibility on the program, and today you will see when we will do exercises that how important it is for you to keep track of all the threads, and why you have to terminate your threads to make sure that one of the thread is just not hanging in between doing nothing, just taking up all the resources of operating system. So it's a great responsibility on programmers when managing threads and using multi-core or multiprocessor system. And then we talk about parallelism. We'll talk about that, what that is, and we talk about concurrency as well. In fact, let's talk about that. So there are 2 concepts. One is concurrency and one is parallelism. So concurrency means that your processes, or in this case, for example, your threads are running, but they are not running at the same time. But since your processor is so fast, it's switching between different threads so fast that as a user you believe or you think that they are all running at the same time. For example, your music is also running, you're working on Word document, you have a browser open as well. So you're doing all the tasks, but as a user you think that all these things are happening at the same time, but it is not happening at the same time. What is happening is one of the threads is running at the same time. Assuming that you have only one processor, single core, one processor, one task can run at a time in that single processor, because you have only one processor, and only one process, in this case one thread, can run, or one task can run at the same time. But since the context switching is happening so fast that your operating system is giving processor to the next task or the other task so quickly that you don't feel any lag. You think as a user that everything is happening at the same time. This concept, when a single core is handling or doing a context switching so fast that the system or that the user thinks that everything is happening on the same time, is called concurrency. They are running concurrent, they are not running simultaneously, they are running concurrently, which means that they are being context switched very quickly by operating system, since there is only one core, one task can run at a time. So it's doing the context switching so fast that we think that everything is happening at the same time. In contrast, there is another concept called parallelism, which is based on multi-core system. Obviously, you have multiple cores. Let's take this example where we have two cores or two processors. In this case, the tasks or threads are being handled simultaneously. So thread number 1 and thread number 2 are running at the same time, but on different cores or different processors. Thread number 3 and thread number 4 might be running at the same time, one on core 1 and one on core 2. So they are running at the same time. So a concept is called a parallelism when multiple tasks are done at the same time simultaneously. And concurrency means when using a single core, different tasks are done in such a way, context switching is done in such a way that one task is done at a time, but since the context switching is happening so fast that it doesn't look like they are happening at the same, they are not happening at the same time. It looks like they are happening at the same time. So this is the difference between concurrency and parallelism. Try to take another example, try to see how it works. I hope it is very clear, because obviously, I mean, with one processor you can have only one task at a time. With multiple processor you can have multiple tasks at the same time. It's not that difficult concept, but you should know. I mean, these words might be not very comfortable, but you can say concurrency or processes running concurrent or simultaneous. This can be another one, but since these are the technical terms normally used by operating system developers, so it's a good idea to get used to these terms, concurrency and parallelism. So I hope this is clear. So now we're going to talk about user threads and kernel threads, right? So just like what we have discussed in our previous lectures about what a user space is and what a kernel space is, just like that we have user threads and kernel threads, and I'm sure by the name you have already guessed what they are. So the threads that are created by user is called a user thread, or user applications are called user threads, and the kernels that are created by operating system or the kernel are called kernel threads. So again, a user thread is a thread that is created by the application, by the user applications, is called a user thread, and the threads that are created by operating system, they are called kernel threads. Very simple. So some of the examples, for example, in Linux or Unix based system, POSIX based systems, P threads are used, POSIX threads are used normally. So these are the libraries, so POSIX threads are used to create threads in Unix based system. For Windows use Windows threads, and Java also use threads. I'm sure some of you have already used Java, and some of you might have already used threads in Java. So Java has its own threads on JVM. And then kernel threads, there are some kernel threads which operating system is managing on its own, and these are obviously handled at the operating system level, like Windows has its own threads, Linux and Solaris and Mac OS, they have their own threads. Now let's talk a little bit about multi-threading models. What are multi-threading models? So multi-threading itself, what it is, we know that multi-threading is something when multiple threads are running, right? Multiple threads are running. So that environment is called a multi-threading environment. Now how to handle these threads? It's important to handle these threads. And since some of the threads, as we just saw over here, some of the threads are run in user space. So these threads are normally called user threads. Some of the threads, they are run in the kernel space, and they are called kernel threads, right? So we can say this like this as well. So any thread that is running in kernel space is called a kernel thread, or any thread that is run by a kernel to manage different things is called a kernel thread. Similarly, any thread that is running in a user space is called a user thread, or any thread that is created or run by user applications is called a user thread. Now sometimes these two types of threads, they need to communicate with each other, and that is very obvious because sometimes, for example, a user application which is Microsoft Word, for example, it has a thread that is required to print something. So if this thread needs to print something, it has to communicate with kernel thread, because kernel thread has direct access to hardware, and user threads, they don't have access to hardware, as we know from user modes and kernel mode as well. So in that case, this user thread needs to communicate with kernel thread. Now how they communicate with each other, what type of models they use, they are called normally multi-threading models. Multi-threading models. You know, there are three types of multi-threading models: many-to-one, one-to-one, and many-to-many. Let's talk about them one by one. Let's talk about many-to-one first. If you see this diagram, what is happening and why we are using this, because some of the user threads, they need to communicate with kernel thread for whatever reason. It can be a printing reason, it can be using some other hardware like disk, it can be any other reason. So different threads, they want to communicate with kernel. So in many-to-one, what happens is many user threads are associated with only one kernel thread. So there is one kernel thread, and with this kernel thread, many user threads are associated. Now for example, there is one process called P1 that has 4 threads like this. In many-to-one, these 4 threads are associated with kernel thread. Alright, that's good. It's not pretty difficult. So kernel threads are associated with user threads, and there can be multiple user threads. That's why they are called many-to-one, because many user threads are associated with one kernel thread. Okay, so this is one of the ways we can connect user threads to kernel threads. Now what is the problem in that? The problem in this, and by the way, who is using this? Solaris Green threads are normally using this concept, and GNU portable threads are using. These are old systems which are still using this. Okay, so what is the problem in this? What is the problem in this? Now the problem in this is, since these 4 user threads are associated with kernel threads, if one of the user threads, for example this one, it blocks this kernel thread, then all of them are blocked, right? So thread 1, 2, 3 and 4, they all want to communicate with kernel thread. They have their own tasks. So this one wants to print something, this one wants to save file on the disk, this one wants to upload a file using internet, this one wants to play music, for example. So these 4 threads, they want to, for example, all of them, they want to communicate with the hardware, and there is one kernel thread that they 4 are associated with. So they all need kernel thread, right? If this one, for example, it wants to print something using kernel thread, and printer is busy already, this kernel thread will then block this user thread will then block this kernel thread, and all of the other one will keep on waiting, because this kernel thread is not blocked by this user thread. So one of the disadvantages of this approach is, if one of the user thread blocks this kernel thread, then all other threads are blocked, because they are just waiting for this kernel thread to get free so that they can get associated with this and complete its task. So this is one of the problems with this one, and it's a big problem. For example, these 4 threads are part of one process now, and since process 1 is now it can only complete when all of these threads are complete. Now in order for that to happen, all of these threads need to communicate with kernel. Now since thread number 1 has a system call with kernel thread, it has blocked this. So the process itself is blocked now. The whole process is blocked because its threads are blocked. So this used to be a big problem, because that time there was no other approach to associate user threads with kernel threads. So developers came up with a new idea. They said, okay, let's talk about one-to-one. Each user thread will be associated with one kernel thread. So if there are 4 kernel user threads, they will be associated with 4 different kernel threads. Now it solves this problem, that if, for example, this thread is blocked, The other threads will not be blocked because they are not associated with the same kernel. They are associated with different kernel threads, right? So they all can run, all of these kernels. For example, this kernel can run on processor 1, processor 2, processor 3, processor 4. So if this link is blocked, then these can still work on different processors. It's absolutely fine. So the process, the whole process, which is actually the parent of all these threads, it still has to wait because this thread needs to complete. Yes, it has to still wait, but then they don't, once this is done, then the process will be completed because these three processes or these three threads are already done with the other, using the other processor, they are completed. So it's, the process is only waiting for this thread to complete. So it's not blocked. Once it's done, the others have already completed, for example, so the process will complete. So in this case, one user thread will be associated with one kernel thread. Now Windows used to use it, Linux used to use it, but obviously they are moving to a better system. Why and what is the problem with this model is that with 1000 user threads you have to create 1000 kernel threads. It's not a good idea to create threads because it's not a good idea to create a lot of kernel threads, and operating systems normally they put a limit on creating kernel threads. So for example, they might not allow user threads to create more than 10 kernel threads, but there might be 1000 user threads. So maximum kernel threads you can create in that case would be 10 kernel threads, and then other threads would have to wait because only 10 user threads can be associated with those kernel threads, and just have to wait. So this was one of the problems, and this was very evident that obviously each user thread creates a new kernel thread, which is not a good idea. Creating a lot of things inside the kernel, it's not a good idea because then you are making it a heavyweight system that would become very difficult to handle, that will become very difficult to maintain. So this was the problem with one-to-one. So how this problem was solved? There was another model called many-to-many. So many user threads are attached with many kernel threads. Normally when we are talking about many, so if there are 4 kernel threads, user threads, if there are 4 user threads, they are attached to 4 or less than 4 kernel threads. They won't be more than 4 kernel threads, right? So if there are 4 threads, user threads, they will be attached to 4 or less kernel threads, not more than 4. Now in this case, how the problem is solved? Now for example, this is associated with a point over here, and we'll talk about what this point is and how operating system decides that which user thread will go to which kernel. So in this case, if this user thread comes, operating system will check which kernel thread is available and it will assign that to that. Next one comes, assign it to that. Next one comes, assign it to that. And since they are running very fast, we are assuming that they will not be blocked. If one of them is blocked, is fine, but if all of them is blocked, then this guy has to wait, obviously. But obviously with multi-processor system, this normally doesn't happen. If this happens, obviously you see that some of the programs are frozen. That's why some of the programs still get frozen in these modern operating systems as well, because some of the things like this is happening in the background. But in this case, all the problems we had in one-to-many and one-to-one was solved, because whenever a user thread comes, if for example this thread comes and it has been assigned this kernel thread, and this kernel thread is blocked because of some reason, then if next kernel thread user thread comes, it can be assigned to this kernel thread. Next comes, it can be assigned to this kernel thread. Once they are done, next one can be assigned to that. So a lot of problem was solved using this, and modern operating systems are normally using this. Now most of the operating systems, they are using this one, and obviously it makes a lot of sense because it takes out all the limitation of having only one kernel thread for many user threads, and taking a limitation of you cannot create a lot of kernel threads. So you can still create many user threads, but you don't have to create many kernel threads. The available kernel threads created initially by operating system, it can be assigned here and there, just like processors. So these are multi-threading models that can be used for handling different threads in operating. So let's talk a little bit about thread library. Thread libraries are basically APIs that are provided to the programmers and developers for creating and managing threads in journal. These can be provided by the operating system itself. It can be provided by an environment as well. So basically there are two types of implementation for these thread libraries. One is the one when the whole library is in the user space. The other one is when the library is in the kernel space. So what it means is the thread library that is provided by the operating system, it is in the kernels, it is in the user space, and user space can actually manage the whole library itself. The other way around is to use the whole library in the kernel space, so operating system has to manage that. Well, different operating systems, they manage it differently, and these days normally three main thread libraries are used for, by different operating systems. So POSIX based operating systems normally use p threads, and we're gonna do an exercise on that today. Then Windows use their window threads, and then Java use Java threads and JVM as well. So these are three main libraries, thread libraries, that are used these days to perform different operations on threads. So let's talk about them one by one. Although we're going to talk about p threads in detail, we're going to program our code in program different threads in using p thread in C today. So what it is it's basically a user level or kernel level. It depends upon which distribution we are using. Based on the distribution, this library is placed either in the user level, user space, or in the kernel space. Then it has a standard. Obviously it has to follow that standard of API for creation and synchronization of threads. This is basically a specification and not an implementation. Implementation is inside the file, and we'll talk about that when we start developing our program. And API basically it specifies the behavior of the thread library. Implementation is totally dependent upon the development of this library. I mean, different distributions use this library differently, so that's why to say it generic, it's very difficult. But yes, it has to follow some standard, and this is the standard followed by all the distributions for this library. And where it is used, it's normally used in almost all of the famous Linux distributions or any Unix based operating system. But outside Unix, it's being used by Mac OS as well, Mac OS X as well. So next we have Windows thread. It's pretty similar to what pthread does. It helps in creating, managing, terminating the threads. But Windows API uses create thread library that is used for almost all the things that you want to do with threads. Then it also helps in security information, managing the size of the stack of threads, then flagging the threads with suspended states or active state, and so on. Then Java also maintains a thread library. I'm sure many of you have already used Java, and especially the runnable interface. It's pretty famous. And this abstract method run, it helps in running the threads. So Java also helps in managing one of the threads library, and this thread library helps you in creating and managing different threads using the runnable interface. In fact, the exercise we're going to do today, we're going to do it in C language, but if you want to implement that in Java, you are free to do that. In fact, I would highly recommend Java developers who are in this course to try and develop the same programs in this library using the runnable interface. So these are some of the libraries that are being used by different operating systems and different environments like Java. Next we're going to talk about implicit threading. So what implicit threading is? Well, when we leave things, when as operating system, if operating system leaves everything on users or developers, it becomes very difficult to manage those things, because different people are going to develop things differently, and operating system needs to understand what user wants or what developers program wants. So implicit threading is a concept where threads are implicitly created, and this effort or complexity of threads being created by the user is actually taken from the user or from the developer. So developers don't have to go to the complicated things behind creating the threads. They can simply use the APIs, and rest of the things, how threads are created, what are their memory addresses, how much space they have to manage, it will be done implicitly, either by the development environment or by the operating system itself. So these days most of the threading is done implicitly. So developers or programmers, they only use the libraries or APIs, and all the complicated thing is either done by the compiler or by the operating system. So this concept of hiding all the things, all the complications of threads from the developer is called implicit threading. there are three different methods of doing an implicit threading. One is through thread pools. One is OpenMP, multiple programming, multiprocessing. Then grand central dispatch, normally also called GCD. So these are three techniques. Let's talk about these techniques one by one. And let's start with thread pools. So what happens with thread pools is whoever is creating the threads implicitly, either operating system or the compiler, what it does is it will create the threads inside the pool when it starts. For example, let's assume that operating system is creating threads for the programmer, then provide a library to the programmer to use those threads. So what operating system will do is operating system will create some of the threads initially and put them in a pool. So how it will help in a way that when threads are required, then you as a developer or the API or the operating system does not need to create those threads again. These threads are already available and those threads can be used by the programs, right? So some of the threads are already created in the pool that can be used by different programs. It helps a lot because when they are required, they not need to be created again. They are already there and they can be used to do anything required by the programmer using the API. So these are called thread pools, where threads are already created and placed inside the pool, and from there from the pool those threads are taken and can be used by different applications or the programs by the programmers. Then the other way of providing an implicit threading is using OpenMP. What it does is it's basically a compiler directive. What it does is it will use a directive inside programs and then it will handle the threading on its own. So what I mean is, for example, if you see over here, what this does is it's a C program. What it does is it's just printing something on the console saying I am a parallel region. If I want this if I want this statement to run in a separate thread, what I'm going to do is I'm just going to write pragma omp parallel. This is the directive of OpenMP in C language. So I'm going to just mention that, and inside the block I'm going to mention the statement which I want to run in a separate thread. That's it. And this statement will now run in a separate thread. And any statements I want to write as a separate thread, I want to run as a separate thread, I'll just place them over here. So very simple way that obviously, I mean, it's pretty complicated when you go to the details of this, but in order to provide programmers a better way of handling threads, we can use this directive of OpenMP. Obviously it's available for C++ as well, it's available for Fortran as well, and I think it's available for Python as well. So this is one way of creating your threads using OpenMP, and obviously these threads, how thread will be created, this is up to OpenMP. Developer doesn't have to worry about that. Then we have a grand central dispatch, GCD. This was developed by Apple, and Mac OS and iOS they normally use this GCD. So, and this Apple was kind enough to provide the extensions for C, C++ language as well, and this is available as an API. GCDs are also available as an API for C and C++ programming languages as well. Just like OpenMP, it does something very similar, although the details behind what is happening with threads, how they are created, it's different than OpenMP. If you want to read more about it, just try to Google that, but since it's it's beyond the scope of this course, I'm not going into the detail. I'm just going to tell you how it works. So in order, for example, same thing, if I want to run this specific statement in a block, in a thread, what I'm going to do is I'm going to use these keywords. So I'm going to use this cap sign, then the block start, and then the block end, and anything inside this block will run in a separate thread. This is how you use GCD in any programming language, either it's C language, C++, or Objective-C, which is used by Mac OS and iOS. So if you want to run a statement in a separate thread, what you're going to do is you're going to just use these keywords, and within this block you're going to write the statement which you want to run as a separate thread. So this is how GCD works. And obviously GCD runs on two different commands. I mean, one of them is a serial command and the other one is a concurrent command. What serial command is, basically GCD is maintaining a queue. It maintains a queue. So anything, so for example, if I have 5 statements, all of these 5 statements that I want to run in different threads, they will go inside a queue. And there are two types of queue. One is a serial queue and one is the concurrent queue. In a serial queue, everything is removed in first out order. So whatever comes first will go out first. So anybody in the front of the queue will leave first. So if I want to run one of my statements and there was nothing in the queue, I will put that statement in the queue, and all the statements come after that, they will be after that statement in the queue, and first thing that will be entertained by my GCD will be my first statement which was in the queue. But this is done one at a time, so each statement is taken out one at a time. In concurrent, what happens is normally it still offers FIFO, first in first out, but multiple statements can be removed at the same time because of using multiple processors. So 3 statements might be removed out of 5. One goes to processor 1, another to 2, another to 3, and it works like this. And obviously sometimes there might be some priority, so there is a default priority which just uses FIFO in normal way. Then there is a low priority of something that is not required right now, maybe required later. We can put a low priority on that and it can go to the end of the queue, and something with the high priority at the end of the queue can be brought to the front of the queue, and then it can be entertained. So these are two types of dispatch queues normally used in Grand Central Dispatch GCD, but we are not going to work on that. We're going to work on P threads, and we'll see how threads are implemented over there. Now the last topic as far as theory is concerned, again this threads topic is so comprehensive, it's so huge that I can talk about it for at least 3-4 hours very easily. But again I want to make sure that whatever I am telling you, we are implementing that in our exercises as well, so that you actually understand what and where they are implemented. So for some of the things I cannot jump them, for example GCD and these implicit threading, I need to tell you that, although we are not going to implement that, but I have to tell you that because you need to understand why threads are how threads are managed implicitly by different operating systems. And again there are some thread issues that you need to know when you start developing your programs using threads. And not only as an operating system developer you might use threads, even if you are a normal programmer or a web programmer, you might end up using thread somewhere. So you need to understand what can be issues behind a thread. So let's talk about the issues, and once we are done with issues, and it's not going to take too much time, we're going to move to our practical exercise. And before obviously moving to practical exercise, I'll explain you the assignment, or maybe I can explain assignment after we are done with the practical exercise. So let's talk about issues. What issues can come when we are dealing with threads? So the first issue that can occur is the fork statement. We know fork statement, right? Fork statement is used to duplicate your processes, right? So if I want to split my parent process into a child process, I use fork, and we did a couple of exercises last time also for fork, and I'm sure you guys understand how fork works. So when fork is applied on threads, how does it behave? It's very important to know that. So if I have a process P1 that has 2 threads, and on thread number 1 I apply fork. So how does it work? Since fork is applied on processes, both of my threads will now have separate children, a parent and a children. So for example, I end up having 2 different streams for thread 1 and then 2 different streams for thread 2. Is it gonna work like that? Should I end up having 4 different threads after that, or should I have only 2 threads, since only one of the threads called for fork and the other thread did not call for it? So maybe thread 1, since thread 1 has called fork, so only it should be split. Thread 2 should not be splitted. So how does it work? I mean, what are the semantics of using fork? Well, in Unix it has 2 versions. One version is for splitting all the threads in your process, which can be expensive, of course. So if there is one process, process 1, and there are two threads, T1 and T2, if you use fork on any one of these threads, all the threads will start having a fork now. I mean, all the threads will start having a parent and a child. So separate, they will be separate streams, 4 of the streams in this case. Then Unix also offers another version of fork where only the fork that called for fork, only the thread that called for fork will be splitted into parent and child, and the other thread will remain without splitting. For example, again, process 1 has two threads, T1 and T2. T1 called for fork system call, then T1 will be splitted into parent and child. However, T2 will not be splitted. T2 will remain like that. So Unix provides both the flexibilities, and this is how fork works in threading. Now it depends which version of fork you want to use, and for that I would highly suggest you to see the documentation. I'm not going to go there for now. And then there is exec command. I think I quickly explained this last time to you, and then I ask you to review it yourself. What exec does is, if I have a process and if I have a process P1 that has ID 123, and I call exec command inside that process, what this does is it will give another task to the process, but the ID of the process will remain same. Again, let's do that again. So what exec does is, I have a process P1, and that process P1 is just printing something on the console. But then I call exec inside the process, and I say don't print on the console, just print through printer. So what this exec will do is, it will replace the printing of console by printing through the printer, but the ID of the process will remain the same. So it will not have a different ID, although the task is totally different, but the task of one of the processes will be replaced with the other process, but the task ID will remain same. This is what exec does. So same thing, same issue is with the exec, the same issue what we had with fork, how to handle them with threads, and I'll leave it to you also. Just go through Google, because honestly I should not hold your finger, your hand, and take you with me for everything. You are third year students, almost all of you, and you should be able to search here and there about different concepts. Don't just continue with these slides only. I mean, I don't want you to simply just go through these slides and then just go through the video and think that everything is fine. I really want you to go through beyond these slides. I mean, go to internet, go to our textbook, and see if you are not understanding something. I was not able to completely convey the message to you. You should at least go to internet or go to your textbook and see how it works. That's why few things I intentionally leave behind for you guys to look, and these can be important. I can ask you maybe this in exam, what exec is, what exec command does, how threading issue can be resolved in exec. So you should be able to understand these concepts even if I don't explain in the video. Please make sure that, and even then if you don't understand that, please come back to me and discuss with me what exec is. Before discussing the concept, you should you please explain me how you have worked and you are not able to understand this, and we can discuss this, right? So please try to see this yourself, and if you don't understand, please get back to me and I can explain it to you in detail. Maybe we can do an exercise on that as well. So this is this thing. Next is signal handling. Normally signals are used in threads to notify a process that something has occurred, right? So it's normally used for that. So a signal handler, in order for the operating system to tell the process that something has happened, it normally provides a signal handler for that, and obviously there are APIs for that. Now what signal handler is used to do is it just generates a signal in case of particular event, and that signal is, first of all, the signal is generated whenever something has happened. For example, you have read something from the database. The thread has been reading something from database for quite some time. Now the reading has complete, an event has generated. You need to tell, as a thread, you need to tell operating system that I am done. So once this is done, a signal is generated, and that signal is then delivered to the process, telling the signal, telling the process, okay, this event has been occurred, or this task has been completed, what to do next. So the process can decide what to do next based on the code written inside the process. So for signals, default handler is the kernel. Kernel handles the default handler for all the signals. However, this kernel handling can be overridden by user defined signal handler. So for example, in your program, if you have written a code for handling a signal, that can be overridden, and that can take place instead of kernel handling all the signals. Now normally when there is only a default thread, only one thread in the process, the signal is delivered to the process because there is only one thread. Even if you handle or give this signal to the thread is going to give this signal to the process. So in case of single threaded environment, when there is only one thread inside a process, signal handling is pretty easy. But what to do when there are multiple threads available? Well, there are different possibilities in that case. In that case, what happens is we need to deliver this signal to the thread that was actually working on something and that required this signal, or a thread that has actually generated a task that required a signal. So in that case, signal will be provided to that thread. Another possibility will be that we give the signal to all the threads in the process. I mean, might not be a good idea, but sometimes it might be one of the requirements. Then deliver the signal to certain threads. If all the threads are not to be engaged in signal processing or signal handling, then this signal can be provided to certain threads inside your process. Now let me give you an example to make it more clear. So for example, there are 4 different threads that are reading a record that are searching for something inside the database. So for example, they are searching for a record of a person who is 38 years old, who is a male, who is originally from Canada, who studied in University of Fraser Valley. So there are 1 billion records in the database, and there are 4 different threads that are reading that are searching for this record in the database. Now, if thread number 1 found this, and let's assume that this process which requires this search to happen has only 4 threads, and all those 4 threads are working on the database. Now in that case, sending this signal to all the threads. So for example, if one of the thread has found the record, then the signal will be sent to that thread. In that case, one requirement would be, since we have found the record, we need to send the signal to all the threads so that they stop searching, because we have already found the record. So in that case, that will be sent to all the threads in the process. So in some cases, this might be a requirement, because if the record is found, we don't want all the other threads keep on searching for something which we have already found. So in that case, this might be the requirements, so that we can send this information to all the threads. Obviously, in some cases, you don't want to send it to everybody. You want to send it to certain threads. For example, 2 threads are working on something. For example, 2 threads are working or searching something from the database. 2 threads are working on something else, and 2 threads are working on something else. Then in that case, what we can do is we just send this information to if the record is found, we send this information to only 2 of those threads that are working on the database. Threads that are working on internet, or threads that are working on images, we don't have to send this information to them. So only to certain threads we can send this information. Or we can have another possibility will be, we have one specific thread that will receive all the signals, and then this thread will do something based on that signal, and then maybe this thread will transfer that signal to some other threads. So there can be one receiver thread that will receive all the signals, and the information, this thread will send this information to the corresponding threadlet. So these can be possibilities when we are working on multi-threaded environment, right? So this is called signal handling. Now another issue that can happen in threading is thread cancellation. Why thread cancellation can be an issue? For example, first of all, let's talk about what a thread cancellation is. Thread cancellation is when a thread has not exited on its own and we had to terminate it because of some reason. So thread was still running, it has still not completed its execution, but we had to terminate or cancel it. This is called thread cancellation or thread termination. We normally call it thread cancellation in technical language. So this is what is called a thread cancellation, right? Now, why would we require thread to cancel? Why would we want a thread to cancel? Well, as I said earlier, I gave you an example earlier. There are 4 threads running inside, running and searching for a record in the database. And one of the threads one of the threads has found the information. So we need to cancel all 3 other threads. We can cancel them, right? So this task has been completed. We don't want all other threads to keep on searching the information, so we can cancel those threads. This can be one of the reasons, right? And this can be one of the many reasons. So for example, another reason will be a thread is looking for a resource, but then the requirement for that resource is not anymore. So we can cancel that thread because we don't want that thread to keep on looking for the resource, right? So these are the thread cancellation, and these are the reasons why we might require threads to be cancelled. Now there are 2 different approaches for cancellation of threads. One is a straightaway termination of threads. We normally call it asynchronous cancellation as well. So we can straight away terminate a thread if not required. Now user program can do that, operating system can do that, but since we are talking about user threads over here, so if a thread is not required, just as I gave you an example, it can be immediately cancelled and thread will be terminated. The other one would be thread is doing something, and we have programmed our threads in such a way that they keep on checking whether they should be cancelled or not, right? So let's go back to the database environment where there are different threads that are searching for a record. Now these threads were periodically, these threads will periodically check back with the process. Has the task completed? Has some thread found the record or not? They will keep on checking with the process. If somebody has found it, then they will self-terminate themselves. They will cancel themselves. If record has not been found, they keep on searching, right? So this is called a deferred cancellation. In that case, threads will keep on periodically checking whether they should be cancelled or not. So if a situation is reached where they should be cancelled, what they do is they self-cancel themselves. So somebody else from outside needs not to cancel them. So these are the 2 approaches which can be used for cancellation of threads. Now there can be another issue with threads, that is the local storage. Now each thread maintains its own data, as I showed you in the stack. It maintains its own data, and it's pretty useful because in that case threads can use their own space and they don't have to wait for other threads to stop using a space in the processor's memory. So they can maintain their own space. So this space can be static. So each process can have its own space. But then the problem can occur that maybe a thread needs more space than what is given or allocated to the thread. In that case, well, obviously solution would be to request for more space from the process, and process will request operating system to provide more space. So sometimes threads are given, since they are very lightweight, they are given their own space, but sometimes threads are looking for more space than required. Now this is the responsibility of the programmer or developer to provide threads, write a code where the appropriate space is provided to the thread, so that they don't run out of memory, they don't run out of storage. So this can be one issue, and this can be solved in a way by the programmer by providing an appropriate space. Then there is a scheduler activation. We have talked about different multi-threading models. So let's assume that there is a user thread that is associated with kernel thread, or maybe there can be multiple many-to-many relation or one-to-many relationship. In that case, if we go back, maybe we can explain it. If you see this over here, we have this dot. This is basically a scheduler. What it does is this scheduler is actually handled by operating system. What this does is this scheduler will see which kernel thread is now available, and I can assign user thread to which kernel space. So this is basically that one. So this is actually used by or handled by operating system. Now since this is handled by operating system, it needs to make sure that it has all the information of kernel threads, it has all the information of user threads as well. So again, I mean, this is one of the ways, right? Now what can be an issue in this is how many of these to create, how many of these to be created. I mean, one is enough or two are enough. How many should we create? It depends basically on the environment. It actually depends upon your operating system as well. Some of the operating system, when there are, let me go back to that diagram as well. So some of the operating systems, what they do is when they have multiple kernel threads over here, they have multiple schedulers over here, so that if one scheduler is busy, other scheduler can take the task. Now it depends upon the environment. Some of them they use only one of them, some of them they use different of them, so it totally depends upon the environment. So these are some of the issues we have in threading, and it is important to know what these issues are, what these issues can how these issues can be handled, and what major issues can these issues bring up. So it's very important as a developer, because you are going to use threads and you are going to create your own threads in your program. So it's very important that you as a developer know all of these issues and handle these issues before they are actually gone into implementation or gone into execution, because operating system will take it, and operating system on the behalf of your program will work on your program accordingly. So these are threads in general. We have talked about threads, we have talked about the differences between threads and processes. We have seen what multi or single threaded processes are. We have seen multi-core programming as well. We have seen concurrency and parallelism, what they are. We have talked about them. We have talked about user threads and kernel threads. We have also talked about multithreading models as well. We have talked about different libraries that are available, and then we have talked about implicit threading, and finally we talked about threading issues as well. So I will stop here for theoretical part, and I'm gonna create obviously another video for the practical part. Well, I create separate videos for two reasons. One of the reasons is I don't want to bombard you with a lot of these things in one video. I want to give you some break. I mean, you can obviously take some break in between, pause it and take a break, but it always, some of the students might want to go back to the exercises again and again and again, right? So they have a separate video for that, and they can work on that. For theoretical part, they can have a separate video. And the second reason is, which is maybe more important than this, is it takes a lot of time to upload and process this video. So if I have a video of 2 hours, one video of 2 hours, it takes a lot of time for processing, because I hope you remember in the first lecture the quality of the video was not proper. So now I'm using a different software, so it takes a lot of time for processing. So it takes around couple of hours, I mean 4-5 hours sometimes, to process in good quality. So that's why I have to create separate videos, so that these videos are separately processed and I can upload them separately and they have good quality. So I'm gonna see you guys in the next video. We will do an exercise, and I'm gonna talk about assignment as well in that video, at the end of that video. And yeah, I'm going to talk about in detail how to do an assignment and so on, so don't worry about that. So guys, I will see you in the next video. Up till then, bye bye.